project, Transformers Learn Temporal Difference Methods for In-Context Reinforcement Learning. Yeah, and without further ado, let's get started. So yeah, I know like in the audience, many of you have seen this interaction at least 5 times. So, but I still want to present the backgrounds of reinforcement learning. So reinforcement learning basically is just learning by interaction, and the backbone of RL is the Markov decision process, where you have an agent that implements some policy that maps from states to a distribution of reactions. So the agent acts according to this policy, and the environment in turn will emit a scalar reward and also transitions to the next state according to the dynamics. And then using this framework, we can define a function that maps from the state to some real value called the state value function that is starting from each state. What is the cumulative future discounted reward will return in expectation? And with this function, we can have some function approximation denoted as v hat that approximates this true state value function using some function approximator and parameterized with the weight w. So how do we get this state value function? One of the most widely adopted policy evaluation scheme is the temporal difference learning, or TD. How it works is the agent generates a trajectory S0, A0, R1, S1, and so on. And in a tabular case where the states are can be represented in the table, we can just do this TD update using each state by bootstrapping. We're computing the TD error. And in the case of linear function approximation, we have some feature function we call phi that maps each state to a real value. And then the state value, the approximated state value, is just the dot product between this feature and this weight. And the TD now is called a Simon gradient TD, where you compute this TD error using this approximated value function, and then times just the gradients of phi st. So that is what we call linear TD in this presentation. And then after I introduce some RL background, I'm going to introduce another concept, which is called in-context learning. So in-context learning, in a nutshell, is just learning in the inference time. So traditionally in the past, we have this out-of-context scheme where we have some model, F data parameterized by data, and we feed in some data set. Let's say F is a number, A is a letter, and then we train this model by tuning this data into theta star, and then giving it some unseen data from the same problem set, let's say 6, we expect it to output a number. So once you train this model with this data set, it's actually problem specific, and it's trained dedicated to this problem. But in contrast, we have in-context learning. What it does is you have a model called G data, and in the inputs, you're not only inputting the query you wanted to give an answer to, but also some context. In this case, in this small matrix, the 5 number, 8 corresponding to letter, these are what we call context. And then we append our query to this, let's say, prompt, to this model, and we expect this model to give an answer as like number for this classification problem. So because it's learning happens in the context, you can switch your problem really as long as it's still classification. For example, if I have a data set called like let's say we are classifying between country and cities, like Canada is a country and then the city. What about Tokyo? And we expect it to output the city. And this happens without us tuning the theta parameter. After it's trained, if you switch the prompts, you should be able to give the correct answer. And this is what we call the in-context learning, as opposed to out of context. So this is a ChatGPT example, really. This simple problem is pretty easy. It's the same prompt. It's the same problem. We give it some prompt in the as a hint, as a context. The 5 is a number, A is a letter, what is 6? It gives us the correct answer as long as some explanation like following it. And it also does the act correctly for this country versus city classification problem. So this is what we've been observing in those large language models. And what does it mean for RL? So how is in-context learning useful for RL? So one obvious application is you give it a lot of features and a reward. Then you wanna like pass it over the transformer and get a prediction of a reward. So this is essentially regression, and it's well supported by previous works. But I guess I think anyone that has experience with RL would think like guessing the reward is not that useful if you're not doing model-based RL. So that doesn't really, at the first glance, it's not that interesting. But we find that if you have a prompt like that, you have the feature for the current state and also the feature for the next state discounted by gamma, and also the reward. It actually can do prediction in the context and output you the value function learned from this the value learned from this context for the feature for the current feature. And how we achieve that? We proved that transformers can actually implement TD in context with linear function approximation. So we have a full proof in our preprint that if you have like an initial prompt as the last slide like that, and you pass through one transformer layer, that is equivalent to one iteration of this batched version of this TD update, where you have WK plus 1 updated by WK plus, the equation is shown there. It's linear TD like update, but it is the batched version because all the updates are summed up and then averaged. So one pass through the layer is equivalent to one step of this batch TD update. So let's say you have 10 layers and you unroll them, it's equivalent to doing TD for 10 steps. And your value prediction will be equal to W10 dotted with your query feature. So we proved that it can does linear TD in context under some special weights. But that is still not very, but that's still like pretty artificial because it only, the construction we have is pretty weird looking, pretty special. We've only proved that they have the expressiveness to implement TD. But how are we going to train these transformers such that it can actually implement TD in context? And that's the second half of our work, is to come up with an algorithm that does that. So what we do is we came up with what we call multitask TD, where you have a transformer parameterized by data, and then we generate a lot of context C, and then we train them also using TD principle. In this case, it's semi-gradient TD, but be careful, now we're updating the theta, the parameters of the transformer, not the weight W. So we're doing equivalently as some meta learning phase to train our transformer. And what we observe is that after we train them for long enough, those weights actually converge to our theoretical construction, which is very surprising because we don't enforce any constraints on those weights. All these parameters are fully trainable, but they choose to convert to TD as opposed to other algorithms. So that's very interesting. after observing that, we try to have some more theoretical justification of this phenomenon. Yeah.
The two figures there, that's, first one is inference. How are those two different?
Oh, these two are just the two matrices that define one layer of a transformer. So the left one or right one are two different matrices for one like transformer attention layers.
Nice.
Yeah. So left one we call it like the P matrix, right? Side is the Q matrix. They're two separate matrices. So in our theoretical construction, the P matrix is supposed to be all zero except for the bottom right entry, and the Q matrix has some two sort of identity matrix looking, but they have opposite signs on the upper half of the matrix. Yeah, thanks for the question. And then we try to justify why transformers implement TD in context. So we have some preliminary results on that. So we proved that our configuration is an invariant set of the expected multitask TD update in the single layer case. And we wish to scale our theory up to extend it to multi-layer case in our future work, as well as some like maybe some more like almost short convergence, maybe. But yeah, we'll work on that in our future work. But now we have like a theory for a single layer. And what's more is that we also proved that with the analogous construction, we prove transformers can implement even more policy evaluation algorithms. For example, residual gradient. And one interesting thing about this residual gradient is that we found that with the same amount of free parameters, you can actually implement residual gradient. But training the transformer with multitask TD, it has the potential to converge to residual gradient, but it converts to TD, and that aligns with the wisdom, conventional wisdom of the community that TD is generally preferred over residual gradient for predictions. I mean, also prove that we can also do TD lambda with some alteration on the masked like matrix. So what I have shown you is TD0 construction, but we also have construction for TD lambda. And then with two head attention and a placeholder role, we call it the memory role. We can actually implement the average TD, average reward TD algorithm. So one head basically is responsible for generating this average reward, and the other head is doing the TD updates, which is pretty interesting. And we have a preprint out right now, and the work is done with my lab mates Ethan Blazer and Hadi Danishman from MIT, and my advisor Shantong Zhang at University of Virginia. And yeah, thanks so much for listening, and I'd like to take any question from you guys. Yes.
So I think when you use transformer, usually you include a sequence, but there's a matrix, or you include this into the transformer.
Oh, you mean
there's a two row, right?
Yeah, so basically this matrix is your prompt, right? So your prompt, like each column is this each column is basically a training pair, right? So this is a sequence. So it is.
So
yeah.
You put it as a batch, and each.
Yeah, it has to have the fixed length, right? So
what about the red one? Is the red one also given to the transformer, or it gets prediction?
Oh no, it's the so yeah, so maybe I skipped too much. So basically, so this is after one layer. After one layer, the first two like feature rows are preserved, but the bottom row is not very interpretable, except for the bottom right entry where you read this off as your value prediction. So this is the output, the transformers output. You want to read it out. The rest are just temporary, like not very important. Yeah.
So well, the first two rows the same after the transformer layer.
Yes, in the theoretical construction it is, but in the training it has some noises, so maybe they're not that not exactly the same after that. Yeah, depends. Yes, Mr. Rich.
So, I'm a little bit confused. I don't really understand. I don't think it's me, how can I, part of my confusion is I don't think of transformers as a learning outcome, because it was a representation strategy.
Mhm.
And said, and, but you seem to say that you're learning the key.
Yes,
So I don't understand, doesn't make any sense. Representation strategy doesn't learn anything, it just is a representation.
oh, it's just the, so after we train this, you can think of our training as some meta learning
If
strategy.
you train, you have to have an objective.
Yeah, so
Transformers are not objective.
no, transformer not objective. So what we did is but transformer can be thought of as a function, right? What we're doing is let this transformer as some function approximator, but also takes in some context. So in that way, we can train it to do prediction problem.
So where do the targets come from?
Targets. Do you mean the bootstrap target or the? So for example, in this case, we have some we use some like randomly generated market reward process, like Boyle's chain. And then it has some so we enroll it, then we generate some data. Then we use this data as a prediction problem to train this transformer to do prediction. And we use bootstrap.
But your goal just to predict. Don't get it bootstrap. You get it bootstrap.
Yeah, so this V, you can thought of as a
Separate what is given and what is learned.
okay. What is given is so we have some transform random initialized transformer. We have some randomly generated market reward process, and we want to train this transformer to predict the value, state value.
So you have many randomly generated.
Yeah, we have many randomly generated market MRP, and we train it to adapt to every one of them.
Same
Transformer. Yeah, we switch the MRP once in a while, and then but the same transformer, and so this is
These different markup reward processes they all have the same input and output space.
what we did. It has the same number of states, so we shuffle the transition probabilities, we shuffle the rewards, and also like shuffle the feature representations. Well, our features are also randomly generated in this case.
What do you ask it to predict?
To predict the state value for like.
You mean you ask it to predict the return?
Yes. Predict the return for.
How do you do that? How do you, the return is only available at the end of activity. So. How do you ask it to predict the return accurately? What's the, is it doing TV we begin with and?
Yeah, so it has some context, right? So it has some information about the specific MRP.
I totally lost that. I didn't understand things like in context, out of context.
So out of context, if you're out of context, what you know
What's the normal case?
the normal case is you have one problem, one MRP. And you use a transformer to map from each state to the state value. We do that by running it using TD to tune its parameters. Using bootstrapping, like using and the hard is normally bootstrapped. But in our case, it's the same thing, but we have another context. And this context belongs to some MRP, which is the same like across this equation, and the reward is also from that MRP. So during this TD updates, everything is from the same MRP. It's just now we switch our MRP once in a while. So the context is gets switched out, the context switch to a different one after we have a MRP switch, and then it's been trying to learn how to approximate the state value function from context for any MRP. This is what we're trying to do. And we do that by using TD training. Okay. This.
So the transformer will be updated. Like using the weights will change.
Yeah, during training is gonna change. The data is the parameters of the transformer.
When I first say this topic, I say this in context. So yeah, I think it will be trained. Just use it. So in fact, it will be trained.
Yeah. I mean, we have the theory, it gives the construction that precisely do the batch PD updates in context, but we also want to train it such that and find out that it really converges to our theoretical construction that does batch PD. So there is a training phase in this.
So what does the context mean here?
In context means you're basically you're doing TD in this C, right? Here, you're not only giving it the problem, you're also giving them huge buffer of context. What you expect is that the transformer using this context information to do PD on this and learn some weight value that's doing linear function approximation, and then that implicitly learned weight is solved with this by S to give you the value prediction of this. And you enroll it for many steps. It's equivalent to do this updates that many steps.
How do you think of this? I don't like supervised machine learning. Tuple and the value. Your examples earlier about A is a letter and 5 is a number.
Yeah. So yeah. So previously this in-context learning was done on supervised learning. So they proved that the transformer can implement gradient descent in context. So what we've shown is because TD is not a gradient descent algorithm, it's not a gradient descent to any objective. So what we're proving that it can also do TD in context and using TD to learn some weights for linear function approximation that approximates the state value of the query state.
On the same trajectory. I usually think about express machine learning as some distribution which examples are drawn.
Yeah.
Like in much of RL's the world changes. You can find new environments.
Yes.
They make IID assumptions of the data here. Or is it?
No, we don't assume IID. They can be the Markovian. Yeah. Yeah. The thing is, right now what they have is a batch version, so it doesn't matter if it's IID or Markovian anyway, because it will always be this will be average then. But for TD lambda, it doesn't matter because we want to have some trace. These columns have to be temporally correlated. But for TD0, this can be novel and it shouldn't be any different. Sometimes the confidence.
which is the experiment.
Yeah, sure.
Do you have the two figures here and you said the ways kind of merge to that correspond to the TD? So essentially, what do we learn from this experiment?
So what we learned is, so this multitask PD, when we train this, what we expect is this transformer learns some, like come up with some mechanism that take advantage of this context to make a good prediction of the state value of your very state, right? We found this using this training maximum. It actually converges to our theoretical construction. Like that. Whereas it can influence any random or unknown prediction algorithm that uses this context for prediction. What we found, it implements TD at the end. It can implement residual gradient with exact to the same like the exact same matrix like with the exact same like three parameters, but just a little bit different of the construction of these two matrices. You can implement residual gradient, but it converts to TD. So that's very interesting.
So if I just take these two matrices and I implement the transformer and I fit in another MLP randomly generated and
Yeah, it will perform exactly that yeah, TD like on the context and then give you a prediction for your query. Okay. There